Professor Nagataki from Sabah. To speak on theories of massive star explosion.
की लैपटॉप कूल लैपटॉप है
massive star explosion.
फोन एटा पूरा बेदोड़ा टॉपिक टोटल एटा
Astrophysical
सुपरनोवा ब्लैक होल.
Thank you very much for your kind invitation, and I'd like to thank the organizers, all of you, and for your hospitality. This is my first visit to India, and I found that India is a very nice country, and I am enjoying the very exciting meeting. And thank you very much. And especially, I'd like to thank the Satoruchi for helping me to a lot to get my visa from Japan to India. So today I'd like to talk about the massive star explosion. And I am from Japan. And I'm from Riken in Japan. And Riken is here. How we can use this? Pointer. Okay. And I'm from Riken, and this is a main campus, and this is a building in our where my offices are, and this is my office. And I moved to Riken from Kyoto University 6 years ago, and in 6 years I hired 17 postdocs, and now 5 postdocs are working in my laboratory, and 12 postdocs get the next positions successfully. I cannot tell you today all of our activities, but I would like to focus on our studies on massive star explosions. And the people in red are main contributors to this talk today. Okay, so let me go to the central engine of core collapse supernova, and a massive star explodes. Okay, thank you. So massive stars explode, and this is an example of massive star, Betelgeuse and Antares, and probably you cannot see the sun. Sun is a point. So this is the radius is 1,000 times greater than the radius of sun. And such massive stars can explode. And human beings really saw such massive star explosion. So historically, there is a historical record in Japan too by Fujiwara Taker, and he wrote about the phenomena of supernova explosion. He saw some star appeared suddenly, and it disappeared and quickly. And now we have a good telescope, so we can pin down which star exploded in Fujiwara Taker's period in 1064. So this is a remnant of the supernova explosion that the writer saw 1,000 years ago. So currently we have good telescopes, and we know that we observe 1,000 supernova explosions that are happening in the universe. So observationally, we know that massive stars explode, but why? So that's our question. So the mystery why massive stars explode is a very long-lasting problem over 80 years. As far as I know, Zwicky and Bade pointed out about the mechanism of the supernova explosion. So they concluded probably supernova will be happening when an ordinary star collapses into a neutron star. So this is the first paper as far as I know. But after that, many people try to simulate, prove their conclusion by using numerical simulations. But more than 50 years, nobody succeeded to reproduce the supernova simulation in computers by numerical simulation. But recently, one of my postdocs, Dr. Takiwaki-san, got a very nice result that supernova explosion really exploded numerically using the K computer in Oregon, which was the fastest supercomputer in Japan and in the world in 2012. And such supercomputer, we found that such supercomputer is necessary to understand why massive stars explode. So this is an outline of the massive star explosion mechanism. And so massive star has an onion-like structure, and inside iron core exists. Because due to the nuclear burning, massive star support its self-gravity. But nuclei, iron is the most stable nuclei, and it cannot sustain its self-gravity by nuclear reaction anymore. So gravitational collapse happens. And this core collapses suddenly, and at the innermost region, a neutron star is formed. The neutron star is a kind of nuclei, and it is very stiff. So gravitational collapse is stopped, and a bounce happens, and a shock wave is formed. And from the neutron star, lots of neutrinos are coming out, because self-gravity is released by the gravitational collapse. Then the gravitational energy is converted to neutrinos, and lots of neutrinos are coming out from the neutron star, and the surrounding matter is heated up. Then finally explosion happens, and the neutron star remains at the center. This is an outline of the explosion mechanism, but this is not enough. This is a very rough sketch. Okay, so I would like to explain the same thing using a real numerical simulation, assuming a spherically symmetric. Okay, so this is we call 1D simulation. One-dimensional means radial coordinate. We assume spherically symmetric system, and we calculate the dynamics of the supernova explosion from using a very realistic massive star model. And okay, this is a radial velocity, and this is a negative. Negative means collapse happens, and this is a radius. And this is at 1 kilometer, 10 kilometer, 100 kilometer, and 1,000 kilometer. Now iron core has 1,000 kilometer in radius, and the gravitational collapse is happening here. And this is a density, and the density increases, and it reaches to the nuclear saturation density. And this is a fraction to nucleons, and the electrons, and the neutrinos, and the electrons and the neutrinos, and the total lepton number. And this is a adiabatic index, which represents the equation of state. So at the innermost region, when neutron star is formed, neutron star is very stiff. So the matter becomes very stiff. Okay. This is a very important point. So I'd like to explain the same thing using a different figure. Okay, this is a radius, 1 kilometer, 10 kilometer, 100,000, and this is a radial velocity here. So okay, gravitational collapse is happening, and this is an entropy. entropy is formed by making a shock wave. So by making a shock wave, temperature is increased, so entropy per baryon becomes high. So this represents a shock structure. And the bounce happens. However, as you see, if you do the one-dimensional simulation, successful explosion is not happening. Okay? So radial velocity is still negative. Negative means gravitational collapse is continuing. So no successful explosion is happening if you do the 1D simulation, one-dimensional simulation. Okay, so this is because Raman pressure and cooling effect prevents the successful explosion. Okay, this is a velocity structure. So this is a radial velocity, and the shock wave is here, and it wants to move outside. This is a radius. Okay, and however, matter is coming into the shock region because massive star, and the innermost region shock wave is formed, but the outside gravitational collapse is happening. So huge Raman pressure is coming into the shocked region. So that prevents the explosion. Also, the upside matter from the upstream matter is composed of iron. However, by passing through the shock wave, temperature is increased. So iron is photodissociated into light neutrons. This is a serious cooling effect. So it absorbs heat. So explosion does not happen due to the Raman pressure and photodissociation. On the other hand, this part is pushed by the nuclear force. I mean, the strong repulsion by the neutron star formation, as well as neutrino heating from the surface of the neutron star. So this is a serious power balance between heating effect and cooling effect. But if you do the 1D simulation, cooling effect dominates and no successful explosion is found. That was a situation that lasted for 50 years or more than that. But recently, our postdoc Takiwaki-san did a very nice three-dimensional simulation using a K computer, and we found that the convection is very important to enhance the heating effect. So convection conveys the heated matter to upside, and the shocked region is heated up by the convection effect. This is the third effect. So this by adding the third effect, we found a successful explosion. This is an example of our successful explosion model. So neutron star is formed here, and the entropy per baryon is shown in colors. And this is a shock wave. So the radius, this is happening at the very innermost region of the massive star. And the neutron star is here, and from here, lots of neutrinos are coming out, and it heats the surrounding matter, and the convection happens if you do the realistic 3D simulation, and successfully explosion happens. That's what we found very recently. So if Betelgeuse will explode in the near future, by Super Kamiokande in Japan, 10,000 neutrinos will be detected. And the gravitational wave will be also detected if Betelgeuse will explode in the near future. Also, I would like to note here that if the star rotates very rapidly, explosion dynamics is changed a lot. This is what we found recently. So this is a rotation model so that Takiwaki-san performed. And this is the star is rotating something like this. And again, purple represents the entropy variation, and the yellow represents the heating efficiency. So heating efficiency is very good, and the entropy variation is enhanced. This is a top view. So star is rotating, and polar region, especially heating efficiency is very good. And the spiral model is seen. So what I want to say is that if star is rotating, dynamics is changed, and the resulting neutrino flux and gravitational wave signal will be changed. So if we detect neutrinos and gravitational waves in the near future, we can compare the observations with our simulations. So this is mandatory to understand the explosion mechanisms of massive stars. Okay, so in 1987, Professor Koshiba firstly detected supernova signals by neutrinos by Kamiokande, but the event number is just 10 or something like that. But anyway, this is the first discovery, and Professor Koshiba was awarded for the Nobel Prize in Physics in 2002. And the Super Kamiokande is working in Japan. And so this is the supernova 1987A in Magellanic Cloud that happened in 1987. And now advanced LIGO is working. So if next supernova will happen in Milky Way, also neutrinos and gravitational waves will be detected. And such observations can be compared with our theoretical calculation. This is a luminosity evolution as a function of time from the central neutron star, and this is a spectrum of gravitational wave for non-rotating and rapidly rotating case with the sensitivity of advanced LIGO and Kagura. Kagura is a Japanese gravitational wave detector which is still under construction. Anyway, when the next supernova will happen in Milky Way, gravitational wave signals will be detected from the supernova, which you are waiting for. Okay, so let me go to the explosive nucleosynthesis study of supernova explosion. Of course, we are waiting for the next supernova in Milky Way, but I have to say that event rate is quite rare. Event rate is about 1 supernova per 100 years per galaxy. So we have to wait for a long time. But our life is limited. On the other hand, there are many legacy of supernova explosion in Milky Way, which we call supernova remnant. So this is a real image of real observation of supernova remnant in Milky Way. And maybe explosion mechanism is imprinted on the morphology or composition or something like that in the remnant phase. That's another way to understand the explosion mechanism of massive star. Okay. So that's another approach, and we are doing so. And especially supernova 1987A is a very important target because it happened just 32 years ago and happening in large Magellanic Cloud, not in Milky Way, but the large Magellanic Cloud is a nearby galaxy. So detailed observations are possible. Especially, for example, this is a real observation by Hubble Space Telescope. And interestingly, this is supernova explosion remnant. Okay. On the other hand, surrounding matter, surrounding rings exist, which is really interesting. So currently, many people believe that before the supernova explosion, lots of mass is lost, blown off from the surface of the massive star. And it has a structure, hourglass structure, something like this, with ring. And inside of this, supernova 87A occurred. That's what our understanding. And all astrophysicists believe that. And 87A shows a very interesting observation result. For example, this is a line profile of iron just after the explosion, and it shows an asymmetric velocity profile of iron, okay, with some fraction of high energy, high velocity component, which is 3,000 km per second, which is really unusual. And we have to explain theoretically why line profile is asymmetric and why high velocity component exists. Because this is iron. Iron is at the innermost region, so it is trapped inside. So which cannot naively, if you do one-dimensional simulation, explosion velocity of iron is very small. And again, we found that the three-dimensional effect is important to explain this. I'll be coming back this point soon. And lots of titanium-44 was detected from 87A, and the amount of titanium-44 is 10 to minus 4 solar mass. And if you do the one-dimensional simulation, the titanium-44 is estimated to be 10 to minus 5 solar mass by many authors historically. And again, I would like to come back to this point. And three-dimensional effect is important. Also, neutron star. So, Professor Koshiba found a neutrino burst. So, it is evident that the neutron star was born in the 87A. However, currently, neutron star is missing. No neutron star is found in the ejector of 87A. And where it is, how we can find it. So this is another mystery. And we have some answers for such interesting observational facts. This is a simulation by Anok Watanabe. He came from Max Planck Institute, and he stayed in our group, and he went back to A. And he did a similar simulation of massive star explosion, and this is a neutron star. And if he put the random density perturbation, small perturbation, 0.1% in density, very spontaneously asymmetric explosion happens, and the neutron star moves as a result of spontaneous explosion. And due to the momentum balance between them, he found a very interesting correlation between the neutron star kick motion. These arrows represent the velocity of neutron star, and this is surface of the nickel component, iron component. You can consider. Yes, thank you. So due to the momentum balance, neutron star, when neutron star moves toward this ejector, lots of ejector go to the opposite side. This is what he found. And you saw that the asymmetric ejector structure, so which is made by hydrodynamic instability, called as Rayleigh-Taylor instability, so which is well known. Anyway, shock wave goes to the dense stellar envelope. Deceleration happens, but the heavy component, massive component like iron, has a huge inertia, so it does not stop. So some fraction of iron penetrate the outer layers, and which has a high velocity, which is observed from in 1987A. So 3,000 kilometer, 4,000 kilometer. So this is an amorphous result for the velocity profile for several elements. You can concentrate on this. So nickel decays into iron. So nickel has a 4,000 kilometer per second. So which is very consistent with supernova 87A observations. So three-dimensional effect. So hydro instability is important to explain the observation. Also, bipolar-like explosion is seen in 87A. This is a time sequence of the observation of 87A and the ejector. In the beginning, it looks very spherically symmetric, but finally it becomes like a bipolar-like. Bipolar-like explosion, result of nucleosynthesis is changed because entropy per baryon becomes high in a bipolar-like explosion. So this is my old simulation, old calculation. But anyway, in the bipolar-like explosion region, lots of titanium-44 is produced, which is consistent with the observation of 87A. So let's put my calculation and the anode calculation together. We can derive a conclusion where neutron star of 87A is. So this is an observed line profile. So this is a redshift side and blue shifted side. Redshift means that the matter is going away from us, and blue shifted component is coming toward us. And lots of, you see the asymmetry. So lots of iron is going to the redshift side. So due to the momentum balance, neutron star should be running toward the blue shifted side. So our prediction is that the neutron star will be observed, and that neutron star should be running toward us. That's our prediction. So please remember our prediction, and let's see our prediction will be justified or not by future observation. So I have run out my presentation time, but anyway, I would like to add some slides. So neutron star motion and the ejector motion has an anti-correlation, which is also confirmed by recent X-ray observation. So our theory is very consistent with the recent X-ray observation. And I don't have time for the molecular formation simulation, but so Ono-san did a nice simulation about nucleosynthesis in 87A model. And after that, temperature drops very rapidly, and finally, molecules are formed. So molecule is very interesting subject because it reflects the asymmetry of explosion. So this is observation, ALMA observation, and this is a ring, and the molecule is really observed by recent radio telescope. And it has a very interesting structure. This is CO and this is SiO. The CO looks like to be ring-like structure. And if we have done the molecular formation calculation using a rate equation, and this is the first calculation of molecular formation in supernova explosion based on the three-dimensional simulation. This is still preliminary, but this is the first simulation in the world. And very interestingly, we could reproduce the ring-like structure of carbon-oxygen molecule. This corresponds to the equatorial plane of the explosion. I don't have time to explain this in detail, but the morphology of molecule it's very important to understand the explosion mechanisms. So this is my summary. I have run out my time, so I don't read it. But thank you very much.
Talk. So now it is open for discussion. Any question or comment, please?
Nice talk. What kind of computer do you use, and how long does it take for one typical simulation like this?
Thank you very much. We use K computer, which was the fastest supercomputer in the world in 2011. Now it is still in the top 10 list. And we use K computer, and as well as some supercomputers in Japan. And typically, one simulation requires 1 month for one simulation. So for 3D simulation, we cannot do many simulations. So, but time scale is something like that.
Good afternoon, everybody. Thank you, sir, for your presentation. Very nice talk. I have a very silly and fundamental question. Whether it is a questionable or not, I don't know. Just like we know that Earth is derived from Big Bang theory, there are two big star collision takes place, then only that things pull down and Earth is formed. So Sun and similar stars are basically considered to be the nuclear fusion reaction are taking place. The hydrogen is converted to helium. So those are basically gases, and that's why they are emitting light. So some stars are emitting light. So definition stars are those are the celestial objects that emit light. So why does Earth is also derived from the same unit and it becomes a planet? So what makes the change that it becomes cooled down and becomes a planet, and those are the stars basically. They are emitting light.
I'm not sure whether I can catch your question or not, but so the light of star depends on the initial mass. It's initial mass. Okay. So if stars is formed in massive way, it has to support its self-gravity by nuclear reaction a lot. Okay. So for sun, so it's still small, and the hydrogen reaction is enough to sustain its self-gravity. And when hydrogen burning will end, the sun will die. So no further heat is coming from the sun. On the other hand, for massive stars, lots of nuclear reactions are required, and it has a very huge gravity, so further nuclear reactions happen. So helium interaction and makes carbon. So triple helium reaction makes carbon, and carbon is bound to oxygen and silicon, sulfur, magnesium, blah blah blah. Then finally, iron.
Okay.